Thanks, Jeff. So first of all, I wanted to thank Google for this opportunity to talk to you guys and get the word out there. I've been, squeaky chair, huh? I've been spending a lot of time out on the road lately talking to Java user groups, and we've had a reasonable response. People are pretty interested in what we have to say and do. It's a kind of a paradigm shift that we need to get the message out there, and so I'm just going to treat this like a big group of developers as opposed to trying to talk to Google or something like that. If you have questions along the way, just give me, raise your hand. I'll try to speak up because we are being taped today, but I will repeat your question so that it's on a mic somewhere. And feel free to interrupt as I go. So basically, what are we going to talk about today, right? Well, Terracotta, some of you may have heard, show of hands, has anyone heard of Terracotta before? About half the room. That's cool. So basically what we talk about drop-in clustering, right? We talk about codeless clustering, and all of that is like pie in the sky. And we're going to get into the nuts and bolts today as to what exactly this technology is capable of, how to use it, how not to use it, and we're going to see some demos, source code, et cetera. So it's a technical discussion. By the end of the talk, we have about 50 minutes left. Hopefully, you guys will have a clear understanding of what I mean by transparent clustering or runtime clustering. I'll call it heap level replication. I'll call it JVM level clustering. But what's the difference between that and APIs that you might use to send messages across a cluster of servers? And we'll talk about how that makes development easier. So with that, I like to start with a demo, because I watched Jonas Bonaire, who created AspectWorks, actually works for Terracotta, and the first time he presented Terracotta in a public forum, he demoed it before he said anything, and that seemed to work well. So basically consider, I'm not going to go through much about what you're seeing here, but this window is the clustering hub. It's basically the guy who's doing all the communication back and forth and making sure all the VMs have consistent view of the world, and that the stuff that they're changing is available to other VMs. And if the window at the bottom is another server. This is actually your application server, and this would be a second application server. So Terracotta server up in this window, and two machines talking to it. And if you just bear with me while I start up the demo, sorry. So basically what we're looking at is a drawing tool. One is started, now there's a second one. And what happens if I draw on one, we're talking about clustering, right? So as I draw on one, it shows up in both. And I can click on things that were created in one machine and move them, et cetera. So we're not going to look at the source code to this yet. But what you're seeing is two machines talking. This is a swing application. It's not a custom built or hacked up thing. So we're actually clustering the internals of the swing library inside the JDK/JRE. And so that canvas is just an object that we're sharing, and everything that shows up on it is shared. With that, I'd like to take an aside at this point and say that typically people listening to the Terracotta spiel, if you will, listen to it, especially as a developer. And I come from a developer background, and I see people in the room that I've actually worked with before. And I'm a hardcore coder, and I don't like listening to vendors who are trying to get money out of me. So I like to make the point that Terracotta, as of this December, you guys will see a press release that explains it all, but basically Terracotta is completely free all the way through into production. You only pay us for support if you want professional level support from us as a company. So the technology is free. Why are we doing it? Because it's all about the developer. It's all about giving you the tools to build applications the way you want to build them, but without actually hindering you with trying to find manager approval, budgetary approval processes, et cetera, so you can cut a PO before you engage with someone. And so what you just saw, we'll now get into what has been happening underneath the scenes. So basically, we're going to cover, on the agenda, I keep meaning to fix this. I call it runtime versus the load balancer. That's not what I mean at all. What I mean is basically the load balancer is a proxy for me for the notion of locality of references, where objects can move around a cluster of servers, and they move based on what that server is being asked to do. And the load balancer basically means that we have an operational mechanism for scaling out an application. So we have the notion of scale out versus scale up, meaning a bunch of small machines like a Google network versus a big monolithic Sun box, for example, from the late 90s, the way sites used to get built, like a 6500 or an E15K or 25K today. So we're talking about scaled out, and when we talk about load balancing, we're talking about a proxy for the notion of a bunch of machines trying to work together on a business problem. And runtime versus scale out, we're going to get into how the two conflict with each other. I want to do as much as I can at runtime, and what's the challenges there. Then we're going to talk about APIs and why they're bad. Little throwback to South Park there. I don't want to come off as a sales guy, so when I say bad, I don't mean APIs are horrible, never use them. There are products out there that are older than Terracotta that have been working for folks. You can use them. I'm not saying you're dumb if you do, but in simple terms, APIs will eventually lose to what we're talking about, which is runtime clustering. We'll explain how it works, we'll look at our architecture, and then we'll look at source code for we'll spend a lot of time with Qt, like swing demos, and then I'll get to a non-Qt demo at the end, and we'll dive into the domain model and the source and everything. So in short, the Java spec is very good, right? This is why we want to cluster at runtime, because we want to adhere to this. What do I mean by the Java spec? I mean things like object identity, where if I do map.put foo and then map.get foo comma bar, and then I do map.get foo, then bar equals bar, right? So equality works, object identity works. I'm a old school programmer myself, so I like to think of object identity in terms of C applications, where I'm thinking about heap and pointers into the heap. And if I new up an object, then in the heap underneath the JVM, it's at memory address 0x1234, and it stays there, right? I mean, logically, physically, the VM might repack memory as part of a garbage collector suite, but logically, I don't have to worry about that object moving around unless I start thinking about things like weak references or stuff like that. So object identity is very important, it's very powerful. Why is it powerful? Well, it comes to the notion of serialization versus my domain model. I want to basically create natural business models. For example, people, right? Adam is the father of all people. Cain and Abel have one father, it's Adam. So they are siblings. That's how I think of the problem if I'm in an object-oriented programming environment. I need to make sure that all the underpinnings of that programming environment are adhered to. Extending that from the simple case of equality to coordination, right? Now I'm not talking about objects and heap and memory addresses. Now I'm talking about wait and notify. I spin up two threads. This guy waits for that guy. I want the two threads to be able to wait and notify each other across machines if I feel like doing so, because the notion of scale out is really a deployment artifact. It's really a decision I make as part of my systems architecture as opposed to my software architecture, and what we're trying to do is decouple those. We'll get into more detail on this, but these natural rules of Java should not be broken. So if I'm clustering by serialization, I'm breaking these rules, right? Because if I have an object graph where Cain and Abel point back to a parent, which is Adam, and then I serialize that up, serialize Cain and serialize Abel separately. I'll show this to you graphically, but basically I end up with two copies of Adam, because each one of Cain and Abel deserialized their own notion of their parent. And now Adam is not the same Adam in VM2 where he was one Adam in VM1, which means now I have to go do stuff as a developer that's no longer Java. It's clustering. So scale out is the challenge. Basically, replication infrastructure isn't up to the task. If you want to scale out today, what does everyone tell you to do? They tell you to build a stateless application, right? Well, maybe not at Google, but at the rest of the world, they tell you to build a stateless application, throw everything in the database, is a very Hibernate-centric message, for example. I don't think Gavin King goes out and says, everybody put everything in the database and OR map it. But I do think that people take the tool and hammer everything's a nail, they start OR mapping stuff, right? The other tool that I've seen used a lot is messaging. Let me send a JMS message around the cluster and keep data in sync on multiple machines by serializing it and copying it to all my peers. And this is sort of a poor man's grid, if you will. And so these kinds of infrastructures, messaging, MQ series, was not built to move megabytes of object graphs or to move them very rapidly in succession across nodes. It wasn't built for the kinds of transactionality that the memory model demands. And secondly, serialization is just not fun. So if you're working in a scaled out world, you're serializing your objects all the time, which means you're changing your application so that you can deal with the impacts of the violation of object identity. So if I do serialize foo and ask for a copy of foo, I would write a different application if I'm saying to my data structures, like give me a copy of the thing I put in 10 minutes ago, I'd write a different app than if I was saying, give me a handle back to the thing I put in. It's sort of pass by reference versus pass by value. I don't want the values of things, I want the reference to the thing I created before, right? Otherwise, Java changes. And replication is achieved through serialization, and serialization deals with copies. That's almost the definition of serialization. And we'll get into how that's not fun. And the most important lesson learned I found at running a big production site like Google does is tuning is sort of never ending. You know, I was getting ready for this talk just 10 minutes ago, and I was walking by an area that the developers spend time in, and there was a thing posted up on the wall talking about unit testing and code coverage versus debugging and finding errors at runtime. So dev time workload versus runtime workload. And those kinds of things are nice, they're extremely valuable, but at the end of the day, you're debugging. And what I found is I spent 50% of my day debugging performance type issues, that it was pretty easy to QA business logic, and you knew whether it worked from a sandbox perspective, a single machine, you knew whether it worked or not fairly quickly. Mercury, Windrunner, all kinds of automation tools have existed for years to try and script the testing of user interaction systems. But the back end, the race conditions of like, what if I'm updating on one node and then a load balancer sends me to another node and the transaction begins again? Am I ACID? Am I transactional? How do I know? How do I even test? How do I get two machines to race for the exact same resource at the exact same time? Generally, it's not easy. And most people don't even do it. And as a result, clustering is something that just causes you no end of pain at runtime. So basically, Terracotta is founded on the assertion that you need to cluster in the runtime, not as part of the dev time. The less you embed in your code, the less you have to test. The fewer things you actually try to think of in terms of state machines and race conditions and locks and things like that, the more stable an application you can build from day one. And clustering at runtime is not unprecedented, right? I mean, Oracle clusters at runtime. That's my favorite example. I'll focus on that and we'll move on. But clustering at runtime basically means I have the ability to write the same application whether the operator decides to build the app for one machine and run it on one machine, run it on 2, or run it on 20. The application is the same application. There's no notion of networked SQL in Oracle, right? I don't write a different stored proc if it's going to run in Oracle RAC. I mean, I don't know of any such thing. Maybe something exists. But I know you do a lot of tuning as a DBA to the Oracle runtime, to your SAN or your storage arrays, et cetera. And some of this applies for Google-type applications, and a lot of it doesn't. But conceptually, you have the notion of centralized infrastructure that is black boxed to the application developer all over your data center already. And so I'm not here saying load balancing is a bad thing. You know, load balancing is a great thing. The observation I've made historically is that ops needs a stateless environment. They need to know that they can just shut down a box and another box will pick up what it was doing. They can't run a system that has a run book that is larger than the documentation for the programming environment that the developer was using to build the app in. So if your Java book is this thick, but your run book for an application built in Java is that thick, something's wrong. And that's what happens a lot. And it happens mostly because we build partially stateful and partially stateless applications where operators don't know what they can and cannot do. So the load balancer is good, but the developer is being impacted by the presence of stateless application design. So we want a managed runtime that relieves the developers. What do I mean by relieve the developers? Very simple. I want developers, Terracotta wants developers to build stateful apps, not stateless applications. So don't write to a database unless you're writing business data. I was on a joint interview with Rod Johnson of Spring fame, Interface 21, just last Friday. And he had the most eloquent single sentence statement of what business data is. And that is, if you need it for audit purposes or you need it in a data warehouse for business analysts to query against, that's business data. Everything else is transient. It may live for a day or it may live for a second, but it's transient. The steps you take in a software state machine from point A to point B, like Jeff, who's sponsoring our talk here today, works on Google Checkout. Classic software state machine, finite state automaton. It makes total sense to have multiple states and to make those states durable so that if a user gives a credit card, they don't have to give it again if they hop servers, right? That's transient data though. Which credit card out of your profile did you pick? If they add a new credit card to their profile, that's business data. But if they picked a particular credit card for this transaction, that is transient state until the transaction is complete. And that state, basically, is what challenges developers when they're trying to cluster. And so what we're saying is take that notion of stateful information inside the VM and make a tool for the developer to manage that state in a stateless world where load can seamlessly fail over between machines. The garbage collector abstracts stuff from you, right? I started working in Java in 1994. I think it was 1.0 beta or something like that. And you know, I had reasonable mastery at that point of the notion of heap versus stack to a thread. And I could build an application that ran much faster. I could handle pointers, no problem. And if I hooked in Purify, you know, I'd find memory leaks in a few minutes. To this day, I've seen many companies come by VC desks trying to say I can detect memory leaks or I have a better VM that doesn't leak or things like that, has a better garbage collection algorithm. So Java sort of theoretically set us back. At least we definitely thought it set us back as developers. In 96, 97, 98, people complained about the garbage collector. But today, in JDK 1.5 or with the advent of pauseless collectors, you can write an application that's pretty fast. And why is that? Well, the JVM has more information at runtime than the developer knows. You know, a developer may say, I need to be prepared because the business says this string could be 64 megs. So I'm going to allocate this string on heap in the old C or C++ terms. I can't make it a stack variable. So I'm going to have this string that is available to me that I malloc and I free. Well, it turns out in production use, it only stores 256 bytes of data, which would have trivially fit on stack, which would have made it for a faster application, but you can't tell that when you're writing the code. And so simple things that the developer is forced to do, the runtime can make decisions that are more intelligent based on data-driven information. And we're going to see how clustering at runtime is both possible and how with data-driven information I can make better decisions about what to cluster, when, and where. So the impact of development time solutions. We talked about this already. Basically, everything is based on serialization. Does everyone in the room, show of hands, who disputes that with me? No one disputes that. Basically, everything that clusters for you today serializes data to move it across processing contexts. Fair statement? It's a broad, sweeping statement. I'm sure someone can point out something that...
Well, the way things are done is as we described, but that does not include systems that are based on shared memory.
Correct. Absolutely. I left that out.
Repeat that.
So the gentleman at the front of the room pointed out that the way things work across physical nodes is as I described, but systems based on shared memory don't have to serialize, which is completely correct. In fact, IBM and Sun in 2000 both tried to cluster Java in a transparent manner. How did they do it? They started on the single machine, and they clustered the VM by writing a VM that uses shared memory heap instead of process exclusive memory for that heap. And they clustered threads, they clustered everything. The whole heap, the whole VM was writing its state out to shared memory, which means you could start up multiple copies of an application, and they would work together. Why would you do that? Well, in 2000, SMP wasn't great, small boxes weren't as fast. You could get a giant Sun machine at that point, run multiple copies of an application, spread out across that machine, and get a lot of capacity out of it. The problem they found was only certain types of apps would run in this share everything JVM clustering model. Sharing everything didn't work. Basically, the garbage collector became a full blackout. So if I want to pause the VM while I clean up memory in a shared VM world, everything was pausing. And that wasn't working for them. So they said, okay, we need to write a custom collector. Then they said, okay, now only certain types of business domain models fit naturally in this, because if you do a type for loop with synchronization in it, then you're letting shared memory is much slower than RAM, so you can't get anywhere near CPU clock speeds. So this thing is starting to make less and less sense and has very finite set of use cases that it works for. And they shelved it. Both companies, you can Google for CJVM and you'll get a Google, that's funny to say here. You can get Google, you can check with Google and see IBM CJVM started in Israel in 2000 and stopped in 2001. This isn't an unprecedented business idea, it's an unprecedented implementation of that idea. And so at the end of the day, everyone is sort of, to your point, sir, they sort of have given up on the notion of clustering at this level and have instead said the developer needs APIs.
I say that your comments are all correct and they're particularly relevant to Java and not to other things where you're not restricted by the Java world.
Yes, absolutely. So the follow-on point was that I'm speaking mostly about a Java restricted context, and that's totally true. I'm not thinking about clustering C applications or C++ applications. It would actually be done in largely the same way we do Terracotta, but it would be done at a totally different layer. The reason Terracotta focuses on Java is because the virtual machine is an operating system as far as we're concerned. It manages resources, it manages scheduling, I/O, et cetera. And so from that perspective, you can't buy something from VMware or download something from ZenSource that can virtualize and cluster a Java application, because the JVM is just a black box process. It's basically a virtual machine, just like a VMware instance would be. And so they meaning the community, leaves clustering in Java specifically to the developer, leaves it completely up to the developer. They say, okay, here's some APIs that wrap up and encapsulate serialization, and here's a collection interface, get and put. And recently they've been talking about grids. Show of hands, who here has heard about the notion of a data grid outside the Google context, like these vendors that sell data grid software? Anyone? Show of hands, who refuses to show hands because they don't feel like it today? You were about to raise your hand, right? Okay. So vendors sell solutions out there that they call data grids. And what is it? It's the unit of work or the master worker pattern that subsystems at Google have been highly scalable as a result of. These guys build software that they ask people to use to build applications in this distributed fashion. And what's the notion of a grid amount to in their world? I'm not talking about the Google world because I don't know it that well, but in these guys' world, basically what they're saying is locality of reference is what it's all about. Who accesses the data? Can I avoid moving it on the network altogether? And how do I do that? Well, I ask the developer to chop up the data space. So server 1 works on data 1 through 1,000. Server 2 works on 1,001 through 2,000. If I can ask people and constrain their development into this grid-like model, then I don't need locking and I don't need default data around, and so the impacts of serialization are lessened. I'd like to bring that up because when I talk about APIs as get and put, people who live with these technologies all day long will say, well, no, I have another API. But at the end of the day, when these guys move data, these guys meaning APIs, when API-based solutions move data across machines, across processing contexts, they serialize those objects to get them from one VM to another VM, which means you as a developer have to deal with the impacts. You have to deal with the fact that object identity is no longer preserved, that memory address 0x1234 is indeed your instance of foo, but so is memory address 0x2345. And you have 2 copies of foo, and what are you supposed to do with them? And you have 2 copies because you invoked map.get twice. Make sense? People are nodding along. So how do these things impact simplicity? I've basically covered all this.
One point.
Yep.
In what you just said, you made the tacit assumption that identity was lost in a multiple machine copy example. Didn't say why. And I assume that you were assuming that that's because the objects would have different addresses on the different machines. That's not necessarily true.
It is true when you're using serialization. Serialization does not preserve memory addresses in Java. So the question was...
I'm saying you could fix that.
Yes.
Both with serialization and without serialization. And so then you could then it wouldn't be so much of a problem because with the same addresses you could use simple synchronization or coherency techniques to keep the things updated. I'm not saying it would be cheap, but I was just saying that you could do it. And there are people who work on that.
Right. And so the point was that people can keep objects coherent across machines, keep them in the same memory space, but that's not how tools are built today. The way people build tools is they leave it up to the developer. The vendors who provide APIs leave it up to the developer to reconcile object identity mismatches across machines. And there's only one way to do it that I've seen people do it, which is they move from pass by reference, object ID, et cetera, to a business ID for those objects. So I have the notion of Adam, Cain, and Abel that we've talked about already. Cain and Abel, I assign them inside the constructor a person ID based on a sequence coming out of a system of record, or a file, that being a database sequence or file system, et cetera. So Adam is person 0, Cain is person 1, and Abel's person 2. And then I say that I change my business logic so that application, the way I write the application looks sort of like this, basically. And this is just, at this point, it's basically the way things are done. You know, there are very few technologies that people are using to seamlessly keep a shared view of virtual memory in the OS layer. I know of 3 companies myself, and none of them have gotten off the ground because their technologies aren't scaling, but the concept is completely feasible. But what we're talking about is the mainstream vendors. So if you went and Googled, again, for clustered Java or Java clustering and caching technology, this is what you would find in open source or in the commercial vendor space. And what you find is that you write applications that look like this. So you'd say Cain1 equals new person Cain, and I haven't provided the definition of the humans class or the person class, so just assume that the constructor takes a parent, or there is a constructor signature that takes a parent and a name. And then we put Cain into our distributed map. So a map is a collection we are putting it into a distributed map, which is important because later on we want to get access to Kane. And when we modify him, we have to get him out of the map again. Does anyone know why we have to get Kane out of the map again? Anyone speak up?
You mean retrieve the mapping for Kane?
Yeah, well, you need to ask the map, the distributed map, give me a handle to Kane.
Yeah, because you need the handle to get to Kane.
Right. So the assertion is you need the handle to get to Kane, but you had the handle when you constructed Kane, right? So why can't you just use Kane 1 that you got back from the VM when you constructed the person? The answer is basically the distributed map means, the presence of the distributed map means that any other VM could have changed the object while you're using it. So it looks very much like EJBs. It looks very much like any notion of impedance mismatched data to programming
It
environment.
also looks just like cache coherency algorithms.
Yeah. So basically, Kane, we get Kane out of the map again. We add his brother Abel, assuming there's an added brother routine. And then we have to put him back in the map so that any other VM that wants a copy of Kane gets the copy of Kane with Abel set as his brother, not the copy of Kane with no brother. So this kind of stuff is kind of weird, because if I wrote it in the single VM case, I would have written Kane1 equals new person, map.put Kane, and then I would have held on to that reference Kane1. I would have said Kane1.add brother. Later, I could have done whatever I felt like, right? I might do map.get Kane if I was in another method that didn't have a reference to Kane, but assume we're in the same method here. This stuff gets really weird really fast.
So what happens if two threads on two different machines are both doing this map.put Kane?
That's an excellent question. So the question was, what happens if two VMs or two threads are trying to put Kane on two different machines so they can't coordinate? Well, here the APIs fall apart. They say, okay, I'm just a get put API. You've seen me before behind the collections interface. Now they say, oh, wait, there's no notion of clustering in the collections interface. So now I need to introduce map.lock. And it's not synchronized, but I can, yeah, I lock the map. I can be transactional without locks. I can just say that I'm consistent, meaning the last one in wins, and I have stable views of Kane, meaning Kane either gets into the cluster, sort of like old VI type editing, last person to save, only their changes as a unit get into the file system. So you can do it without locking, and then you have last one in wins. You can do it with locking. Without locking, some of this really doesn't work because you're not just mutating Kane, you're actually mutating the collection that Kane is in. And if the collection's not locked, then you start losing objects.
So give us the good news. Tell us what Terracotta has to say.
Right. So the good news is basically like this. So clustering at runtime, what we're doing, thank you, Jeff. Got to keep moving here. So basically, Terracotta lets you cluster Java applications in a natural fashion, which we call no APIs and zero code. Now, this is a misnomer. There is an API. It's our configuration file, and you're going to see it very shortly. What we're doing is we're doing heap-level instrumentation of the VM so that we see applications' attempts to edit memory. And we see all attempts to edit. We can see any and all attempts to edit memory. It's like a hypervisor slotted into the Intel architecture, but we're slotting into the Sun architecture inside our notion of the machine, which is the Java machine. And so we can see all IOs that this application wants to do, which means I don't really have to understand applications anymore because I can see when they're trying to write memory. And that's really powerful. The only catch is it's only powerful in the hands of a developer, or it's mostly powerful in the hands of a developer. And that's why it's free, right? Because you guys have to be able to experience this power before you say, I'm interested in building applications to this model. And basically, what does a developer do? What is your interface? It's, we're doing bytecode injections, so you're using configuration files to control which objects are clusterable and which ones are not. You're doing configuration directives to tell us which threads signal to each other across a cluster and which threads can only be run locally. You're doing configuration to tell us which locks are clustered locks and which locks are local only. And that's very important because, let me skip this for a second. In this world where basically today, without VM level clustering, I should stay here, sorry. Without VM level clustering, you're basically clustering the VM at the bottom of your stack, or you're clustering the app server, for example, WebLogic Clustered Edition, or WebSphere Clustered Edition, or Tomcat with pooled memory implementation, things like that. You're clustering your app server, then you're clustering your frameworks, meaning you're building stateless applications. If you use struts, for example, you throw a bunch of stuff in the database, and then you cluster your business logic, meaning you deal with all the impacts of serialization. In a clustered world, we keep the VMs independent of each other, and that's an important revelation. Is keep the VM separate and independent. Why? For operations. So they have the unit of infrastructure that they always had before, one per machine or n per machine. And then you cluster just above the VM and make sure that all the layers above are clustered. So let's talk about how that works. Basically, you have bytecodes that look like get field, put field. These are just a sampling. Monitor entry, monitor exit. The get field bytecode takes object, comma, field name. And that is enough information for me to figure out, okay, if VM1 wants access to a certain object and VM2 wants access to that same object, I'm going to see them getting access to that object just by the fact that all applications compile down to the get field call. So when you use the accessor operator, the dot, like person.name equals Kane, that dot operator turns into a get field. Well, that example is a put field. So in the person.name equals Kane, we're saying object ID is the Kane instance of person, the field name is name in quotes, and the value is the string Kane. And so that's what's happening is on a put field, I can see what's being changed. And if I can see what's being changed, I can replicate that change at a field level to other VMs. And on the get field call, I'm seeing which field you need, which means if I don't have it on a local VM, I can go grab it over the network just in time. And now we're going to look at it visually. Basically, this doesn't show up too clearly, but there are two copies of this object graph, and this is not how VMs are built, but this is how I like to logically explain the architecture and the concept from a workflow perspective. And you guys can't see it, but basically, because it's light gray, but this object graph that says root and object, 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 et cetera, is replicated inside the app in the heap. Why is that? Well, because there's a physical representation of your object graph in memory, and then there's a logical way you think about that object graph as a developer. And today, those two are in unison, right? Your physical and your logical line up as long as you don't cluster. And so what the clustering implementation needs to do is sit underneath heap and watch when those arrows get traversed. Watch when your business logic, meaning the methods that are invoked, actually access the fields in your data structures. So in this example, we touched the bottom right object. And in the example, I'm calling it object 5 underneath this root. So first of all, I've introduced the notion of a root. That's a Terracotta-ism. Doesn't exist anywhere else. But it is what it sounds like. So if you have an object graph you want to cluster, you don't even know the shape of that object graph at dev time, right? It could be a list of things plus a string plus 2 integers. There are some static parts to the object graph and some dynamic. And so with Terracotta, you have to tell us the top level structure that you want to share, and then we'll figure out everything that gets connected to it at runtime. So in this example, we've built an object graph, flagged the top of it as a root, and we're clustering 5 objects hanging off of it. Then we mutate the 5th object down at the bottom. What happens in a clustered engine that's declarative like Terracotta is you start building a transaction for that mutation, for that thread, basically, that's doing the mutation on the graph. And you say, okay, what objects are you mutating? What fields are you mutating? How do I know that? Well, I see all your get field and your put field calls inside that transaction block. So I've synthesized a transaction, ID 1, 2, 3, 4, and I'm keeping track of everything you change. Then if you wanted to introduce this to a cluster, all I have to do is basically take that change and push it to another VM, the same object, somewhere else. Now, how do I know which objects align with which other objects across a cluster of VMs? That's why the middle box appeared in the picture. The middle box knows that memory address 1234 on server 1 is memory address 3456 on server 2. And how does it know that? Well, because one of server 1 or server 2 constructed this route in the first place. Assuming no race conditions, it was created one place, which means the other place faulted it in over the network and didn't construct it redundantly. So it actually said, okay, server 1 says, I'm the first server to start up, I'm gonna new up this route, right? The server 2 says, okay, I'm the second server to start up, I think, do I need to new up this route? That's what Terracotta does to this application. And the application says, I wanna new up this route, and Terracotta says, just a second, I have this object already newed up by server 1. So now Terracotta has seen server 1 and server 2 each create the route and knows what memory address they each have for it. And as a central arbiter of the cluster-wide heap state, the Terracotta server knows how to push changes between one machine and another, where we don't have to keep the memory address space aligned at all. And that's how you get a single VM context from an operations perspective and a clustered VM from a developer perspective. So transaction 1234 says, okay, there's two servers in this cluster, server 1 and 2. They're both accessing the same object ID, number 5. So the change in server 1 has to get pushed to server 2. So I glossed over two very important points here, which is one, I can page things in off the network just in time, which means I can get large virtual heaps, right? I can have a 2 gig, 32-bit heap that's accessing 300 gigs of data. I have customers who do that today. They don't bother with 64-bit heaps. They don't need to. They just access address space and things get garbage collected out to the Terracotta server. And if you try to access them naturally through your business logic, they fault in on the fly. The other thing I glossed over is how fine-grained this system is. I'm pushing the field that changes. I call it objects in the image, but I'm pushing fields as they change. And since I have a central arbiter of the cluster-wide heap, I can know which servers are accessing and using, actively consuming certain objects. So I don't have to push the changes to that red object unless another server in the cluster actually has access in its heap to that object. I also don't have to push changes until it tries to access that object, right? I could do it lazily, so I don't have to push out a lot of data to a giant cluster unless the whole cluster is accessing that data.
So what do you do for failover then if that machine dies, you have the same memory and lost?
So the question was, what do you do for failover if server 1, the big box in this picture, dies, and server 2, the smaller box to its right, is still alive? The answer is, you can run a transactional and ACID compliant mode where every change you make to one VM makes it to the Terracotta server before it's acknowledged. So it's sort of like networked memory in that case.
Same question for your cluster server then.
The cluster server can be clustered.
So you depend on each of these JVMs to be reliable. I mean, they cannot. They have to be connected. They have to be available all the time for you to have these mappings work.
In the current version of the product, yes, we're working on the notion of a disconnected mode, where a VM can go away, and then you're talking about mobile Java or internet-based applications. Not meaning internet services, but meaning applications that are distributed like SETI at home. But that's pretty far out. Yes?
I hope you'll talk about performance and scaling a little bit with when it's a good time to get to it, because it looks like the cluster server has to do a lot of work. And
right. So the question, sorry, I didn't repeat the two questions. The first question was about, sorry, I forgot your question already.
You depend on
Disconnected mode was the question. Disconnected mode was the question, and this next question was about performance and scalability, which we will cover. So the Terracotta architecture, so now we're talking about our specific implementation. Why do I sometimes switch back between the concept and the actual implementation that is our software? Because I think at some point in the future, other people will arise to compete with us, and that we're not the only one going to do this, and that there's nothing wrong with the notion. There may be flaws in our implementation. There may be reasons not to use our implementation and our designs, but this notion, this concept works with or without our implementation specifics.
So is the assumption that you have like a database behind this? Is it just like a caching thing?
There's a proprietary file store behind it. It's not a database.
So does everything have to fit in memory, or?
No, it spills to disk. The question was, is there a database behind it, and does everything have to fit in memory? So let's talk about features really fast. I think we covered all this. It's heap level replication, which means I can share almost any graph. I can't share sockets. I can't share native JNI type resources. So if you start accessing shared memory, I have no idea what you're doing after you make that JNI call. So you can't share everything with this. But that being said, we've come across probably no customers who haven't found a workaround. All our customers have been able to work around the restrictions in what we can cluster. It is ACID replication, which means I cannot throw new exceptions or new error scenarios at the developer because it's a runtime clustering. So, and I'm running out of time here. So the notion of clustering at runtime should be thought of like network attached memory, which means that if you're writing to RAM, just like if you were writing to a local file system versus a remote file system, I could give you a general write error. I could throw you a RAM failed to update error, but what would you do with it? In fact, the operating system catches those types of failures and kernel panics in many cases underneath you. So if you can't write to the grid and you need to write to the grid, we tend not to throw exceptions at you. We tend to give operational tuning parameters and hooks for behaviors to be controlled. So like if one VM wants to write to the cluster and can't, then you could decide to just exit that VM. Something's horribly wrong. But you can't catch an exception and do something with it in line in the application code because there's nothing to do. And that being said, the failover between clustered servers in our implementation turns out to be sub-second. So all the clients can reestablish connection, because it's all stateless, reestablish connection to a secondary server and keep going where they left off. And it takes, as measured in our field team, like 250 milliseconds to fail over from a primary to a secondary server. We have ACID replication, meaning you either push a set of changes that a thread has made or you don't, which means there's no world in which one VM thinks it's changed heap and all the others don't see that change. And if the server fails, then a secondary comes online and accepts the change, et cetera. We have central storage, which means you can keep application state across restarts. We have our communication hub, virtual memory, and we can coordinate, meaning it's not just data replication, it's thread signaling, et cetera. And we can show you that in a demo separate of this. So our next demo is a JTable, meaning the Java Swing JTable tool or library. And if I CD to it and start it up, it's hard to tell because the way JTable's built, the way we've used JTable, we're not painting the grid lines, but this is like a Microsoft Excel spreadsheet. If I click in a cell, all of a sudden you see what's going on. So does anyone want to guess what happens when I type breakfast in room B at 9 a.m. and hit enter? Anyone? Come on. Shows up in the second window. Exactly. And so this is very different from the first demo, right? Because as I was moving the mouse in the other demo, I was getting events to repaint the screen and that I've moved the pixels and all of that event by event, which means a developer has come in here and changed the locking semantics such that I type and I don't see the typing in the other window, whereas in the other application that we clustered at the beginning of the talk, that typing, those keystrokes should have shown up, would have been my expectation at least if I were you guys. But here someone has said where I need a coarser grained transaction. I need the field to be reset in the data structure before I repaint the screen, not the, I need certain methods to fire basically. And so with that, let's take a look at the source code.
What happens if you type both at the same time? And then
I can't do it. I mean, it's transactional, so what'll happen is if you could actually race, then the last one in would win. I mean, if you could actually legitimately race, then they'd basically, one would try to get the lock, fail, the other one, hang until the other one completes the update, so the last one in would win, the way this application is coded.
How would that would be an exception then? You try to update it, you can't. How do you handle that exception?
No, because it's not doing any kind of versioning and roll back, roll forward, so there's no new exception. It's just hung. It's like the two of them grab locks in order to write. The two threads on the two VMs grab locks in order to write, exclusive locks. And so one will grab the lock. They've both read the data in order to display it when they repainted the screen. So they won't read the data again on the transaction. If you wanted to implement a transactional system, you could basically add a version field and say, oh, the version I read is different from the version that I'm about to read while in the lock. So you could build closer to lockless architectures. There's all kinds of things you could do. With a runtime clustering solution, we've got the notion of read and write locks. So you could grab a lock that's non-exclusive, even though the VM doesn't have that notion, without util concurrent. You could grab concurrent locks, meaning everybody's allowed in together and last one in wins. It's all configuration driven. So let's take a look at the source code. Basically, you'll notice just a couple of things. There's no import statements for Terracotta library, terracottatech.com, nothing like that. You'll notice that there are just a few things going on. We're instantiating a default table model, which we could guess from the import statements is javax.swing.table.default table model. It's not extended or anything like that. And it's a private field. And table demo, the class, doesn't implement serializable. Furthermore, you'll note that all this thing does is basically start up an event-driven GUI. It doesn't do much. This is the entire application that we just saw. So in order to cluster this, I have to cluster the internals of the Swing library because there's nothing else in this application. So the magic is in the config file. This is our hello world. So we've drastically simplified the config file, not meaning that this isn't the real config file. This is the config file on the screen, but meaning if you took a look at the config file for the drawing tool we saw at the beginning of the session, it would be more complicated. And it would be more complicated by 2 or 3 lines of config. So specifically, what have I hidden from you? It's the repaint the screen trick. Basically, repainting the screen is a coordination effort, right? It's not a data sharing effort. And repainting the screen, the way it's done is through what we call distributed method invocation. So when I run the repaint event on one machine, it runs on all VMs that are trying to cluster. It's a GUI-specific trick. It totally works. It's accessible to the developers. But here, the key point is the field we're clustering, it's called a root. And I described what roots were before, and everyone seemed to get it. So we're sharing the root of an object graph. And lo and behold, it is called demo.jtable.tabledemo.model, which if I backed up to the code, there's a class called tabledemo. It's in the package demo.jtable. So now we're starting to understand that that default table model that's underlined, whose instance name is model, that thing is basically cluster-wide, thread, instance-wide, the same model for all copies of this object everywhere in the VM. If I newed up another one, the way this configuration is written, that constructor call wouldn't fire. Yes?
How do you evolve your classes?
How do you what?
Evolve your classes.
So we are storing everything in an extremely fine-grained name-value pair type system. So evolving classes, the question was how do you evolve your classes, sorry. Evolving classes is really quite easy in some cases, and in other cases you have to flush the cache in order to do it. So this is meant to be a repository for transient data, so flushing the system shouldn't be scary in most use cases. But we do handle field addition, field deletion, field type changing as long as a typecast could be done implicitly. And then we have scripting hooks through Bean Shell for a developer to come in and say if an application is accessing, so version 1 of source code versus version 2, if there's a mutation to the class data that has to happen when faulting into a version 2 container, the mutations can be instrumented into the application through the config file. And that piece of code can be introduced into the application. So now you can handle Because you're not serializing, you can handle version 1 and version 2 of your application logic running in a cluster, no problem. You can also handle different stacks, so WebLogic, Tomcat, and WebSphere clustering the same WAR at the same time. In many cases, yeah. Well, if you change business logic, then you'll end up with the serialization exception. If you change the shape of the class.
You can write serialization code such that it can go out of time.
Yeah. So the last bit of data is the scalability of this model, and the short answer is hub and spoke as a single point of failure, field changes being too chatty, and network overhead to clustering. Those are the general buckets of performance issues. The answer is, in the hub and spoke world, you scale the hub. So we are clustered, we are a grid type solution, we're just doing it in infrastructure, where ops can run a service separate of the developer environment. Field level changes, we batch them. So how do we batch them? Threading, and the Java memory model has a clearly defined window where threads have to have all changes applied before they're allowed into a monitor. We're extending that to the network. So we fault data in lazily, and threads cannot read data that isn't consistent with the data that was updated in another thread in a lock. Volatiles, all of that stuff is a totally different contract. Network overhead, it's basically runtime optimized. So I batch and window all my updates. I can send 1,000 things at once. I have customers who have benchmarked us against API-based solutions and have found that we dropped in, whereas the API-based solution required them to take a week and a half to rewrite their app. When we did cluster their application, we took about 10 minutes to update 30 million objects, and the API-based solution that was serializing deep object graphs did not finish. Took 4.5 hours before it threw an enumi and exited. So and then when performance tuned, that application ended up taking like 54 minutes with the developer-based optimizations. Yes?
What are the limits to scaling size of memory? Is the central store have to fit on one machine? Can the size of the data that you're working on be the sum of the memories on all the JVMs together, or not? I mean, I'm just wondering where the line is.
It's use case specific. So the question is, what are the limits to scale? And the challenge with scaling is there are applications that have lots of data and read heavy. There are applications that have lots of data and are write heavy, and then there are applications that have little data. So if you're read heavy, write heavy to the cluster, that's a unique challenge from the amount of data you're trying to access. And generally speaking, what people do to scale a Terracotta type solution is they chop up the data and window onto it. So one node will only work on a subset of the data, and they do a scatter gather type architecture to get scalability. But physically, the server can fit, you can store as much data as you can deploy disk against the server. So you can get terabytes or petabytes of data onto a 32-bit heap. The largest we've gone is 1.5 terabytes. Well, the customer is moving towards 1.5 terabytes next year. They're doing 300 gigabytes this year. And the last demo, go into an inventory item by SKU and update its price. Meanwhile, someone wants to merchandise that inventory and have a taxonomy to it. So I could have products that show up in multiple places in my store. And so there I need a tree of merchandising departments, et cetera. And so I can see my products by inventory. In this case, we have a tripod, a mouse, a book, and a 1 gig flash card. And I can see my departments. The 1 gig flash card is in photography and in computers, because it makes sense nowadays to be in both. So if I update the price of the 1 gig flash card, enter the new price of memory is always falling. Now it's by inventory and by department. Not a big deal. It's really easy to write applications to do that. What have I done wrong here? And of course, since we're talking about clustering, I start up a second process, inventory 2099, departments 2099 in the second process. That's not the interesting thing. The interesting thing is if I CD into the source code, actually the best thing to do is start up the console to help us make this point. So there's a console that bolts in through JMX, talking to the central hub, gives us all the information we want about our data. I can see transaction rates across the cluster. I can see it per clients. There are no connected clients right now. I killed them both in order to show you guys the source code in this. So what's more interesting is the object graphs. Here are all our routes. There's our store. If we drill in on our store, it's an inventory of demo.inventory.store. It's an instance of one, sorry. So if I CD into demo inventory, there's probably a file, yeah, store.java. So there's my store class. But what's inside that store is an array list and a hash map, and those are called departments and inventory. So if I look inside the store, and I search for departments, there is one new array list. Store doesn't implement serializable or anything. Inventory is a new hash map. You can see in the constructor, I'm populating all the data. So there's a product, I new up a bunch of products and a bunch of departments, and I add departments, I add inventory, and you can see I've added the products both to departments array list and to the inventory map. And so between the console and the source code, I can make sense of what's going on here. If I drill in on the departments, I'll see a department with a string name with a current value books. I'll see products inside that department. I'll see their IDs and everything. So basically, I have a real world use case where I've built a very simple domain model. It clusters readily. I don't have to worry about serialization, no JMS, no database backing, no nothing. And I have all the data in the server, whether I start and stop the processes or not. If I spin up the processes again, the price is still $20.99. And that's basically it. I have a bunch of questions, but we're sort of out of time. So
the server has to know what's in the config file, and how does that happen?
So the question is, does the server have to know what's in the config file? So in development mode, you run a centralized server, or you can run, it's a process, a standalone Java process. You can run it on your sandbox, or someone can decide to have shared development environment. And then each VM that connects when the server's in development mode is allowed to send its own config file. When it connects, it says, these are all my routes that I'm going to share. The opposite is operations mode, production mode, where you install application named configurations into the server, and applications connect, registering their name through a handshaking process, and they can only share and get access to the data the server has told them they can share. Does that answer your question?
Yeah, it sure does. I had a similar question. If you start this thing up from scratch, it's a really big database.
Data set?
Data set, well, whatever
Right.
you want to call it. You gave an example of some customer with
300 gigabytes.
Yeah, right. So how long does it take to start that up from scratch? And
Right.
and what's the lag time between starting up a new JVM and having it, I imagine that's pretty quick. But I was just wondering what's involved in
Right.
changing the state.
So the question is, what's the startup time when you're dealing with massive data sets, both for the server and for the client VMs that are clustered through it? And the short answer is we're faulting things in on demand. So the startup time is, again, use case specific. If you wrote an application that checks for your, let's talk about a cache, like a singleton cache type of pattern. And you get an iterator to your cache and walk through every element of it just to do some inspection upon those elements. Well, if you have to fault in all of those, we'll batch that faulting, but it'll still take minutes to start up what would have taken seconds to start up in an unclustered world. But for the most part, people don't do stuff like that. So we fault in things on demand. The case where the customer is sharing 300 gigabytes of data, their VMs start instantaneously. And in fact, we have a customer, that same customer is now using us to cluster WebLogic instead of BEA, and they're deploying that in December because WebLogic takes a little while to start up in clustered mode. This thing changes it so their startup time is instantaneous. Tomcat clustering is an interesting follow-on too, because Tomcat, when you're using it in a clustered mode, will actually not start servicing requests until all clustered data is cloned into the node from all other peers. So now you've got a peer-to-peer architecture where you have to wait an unbounded amount of time for network conversations to happen before your process even starts. I've come across folks who actually kill the whole Tomcat cluster in case one node dies. They just kill all the nodes and restart them so that there's no handshake that has to occur. And if Terracotta is clustering Tomcat, it starts up instantaneously. There was one other question.
What if the data that you might cluster needs to be accessible by legacy systems?
Legacy systems access is just a gap in Terracotta's product. Conceptually, it can be done. Basically, we've stored objects as name-value pairs, all their fields and all the relationships across objects. So it is possible for us to create an API for legacy systems to get at that data. But for now, you have to write a Java bridge to get at that data.
So what if the systems that use Terracotta, would they use for their data warehousing?
Oh, they use JDBC to flush to a database, completely separate of clustering. So they'll use like event callback type structures with us and basically say when an object changes, invoke this JDBC flush routine. And in configuration, they can decide if the database is communicated to synchronously or async, meaning I change a field, the database has to be updated as part of the field change transaction inside the VM, or the database can be updated later whenever the network to the database is available and however fast the database is consuming those transactions. So I didn't define database as legacy systems. I was thinking like kicks and orbs and things like that. Sorry. Thank you, everyone.